Hi everyone, thank you for being here today. As we stand at a critical juncture in the fight against climate change and environmental degradation, it has become increasingly important to analyze and address the various ways human activities impact our planet. Today, I will take you through an exploration of emissions and environmental impacts, focusing on the PACT methodology version 3 introduced by the World Business Council for Sustainable Development, WBCSD, and its role in monitoring greenhouse gas emissions. We'll also examine the broader distribution of environmental impacts across gases, liquid effluents, and solid waste. Let's begin by understanding the larger context. Every product we use, every service we consume, and every process we rely on has an environmental footprint. This footprint is composed of emissions to the air, discharges to water, and waste to land. These emissions and wastes are not just numbers on a chart, they are the drivers of global warming, water pollution, land degradation, and biodiversity loss. To effectively manage and reduce these impacts, we need robust frameworks that allow us to measure and monitor them accurately. One such framework is the PACT methodology version 3, which focuses on greenhouse gas emissions across the life cycle of products. But while it produces a comprehensive approach to GHG accounting, it also highlights the need to understand how different types of emissions, gaseous, liquid, and solid, contribute to environmental harm. The PACT methodology or product attribute to impact algorithm is a standardized approach to measuring and reporting greenhouse gas emissions. It is particularly relevant in today's world where industries are under increasing pressure to disclose their environmental impacts and align with global sustainability goals. PACT version 3 is designed to ensure transparency, compatibility, and accuracy in calculating a product's carbon footprint. It monitors a wide range of emissions, from fossil-based and biogenic emissions to those arising from land use changes, packaging, and even carbon capture technologies. This makes it one of the most comprehensive frameworks available for GHG emissions monitoring. However, while PACT excels at tracking greenhouse gases, it does not directly address other environmental impacts, such as those from solid or liquid waste. This is a critical gap that we will discuss further as we move through the presentation. We need to understand the importance of understanding the distribution of impacts. Beyond the scope of PACT, it is essential to understand how different types of emissions, gases, liquids, and solids contribute to environmental degradation. Each of these has unique characteristics and impacts. Let's take gaseous emissions, such as carbon dioxide and methane. The primary drivers of climate change and air pollution are those. Liquid effluents, including industrial wastewater and agricultural runoff, are significant contributors to water pollution and aquatic ecosystem damage. Then solid waste, while often localized, has long-term consequences such as resource depletion, microplastic pollution, and methane emissions from landfills. The distribution of these impacts varies significantly across industries and regions. For instance, the energy sector is dominated by gaseous emissions, while agriculture contributes heavily to liquid effluents. Solid waste, on the other hand, is a pressing issue in urban areas and consumer-driven economies. Understanding this distribution is crucial for designing targeted solutions. It allows us to prioritize actions and allocate resources where they will have the greatest impact. And while the PACT methodology provides a strong foundation for GHG emissions accounting, addressing these broader impacts requires complementary approaches such as life cycle assessment or sector-specific studies. In summary, today's discussion will focus on two key areas: the comprehensive GHG emissions monitoring provided by the PACT methodology and the broader environmental impacts of gases, liquids, and solids. By the end of this presentation, I hope to provide you with a deeper understanding of how these elements intersect and how we can use this knowledge to drive meaningful environmental change. Let's begin by driving deeper into PACT methodology and the specific emissions it monitors. Now let's take a closer look at the PACT methodology version 3 and why it is such a critical tool for monitoring greenhouse gas emissions. As industries and governments work towards reducing their environmental impacts, having a standardized and comprehensive way to measure emissions is essential. This is where PACT plays a key role. Let's take the point 1 we are talking about: comprehensive GHG emissions monitoring. The PACT methodology is designed to provide a detailed and comprehensive approach to greenhouse gas emissions monitoring. It doesn't just focus on one stage of a product's life cycle. It examines emissions across the entire life cycle, from raw material extraction to production, use, and disposal. This methodology ensures that no significant source of emissions is overlooked, whether it's fossil-based emissions from energy use, biogenic emissions from organic materials, or emissions linked to land use changes and transportation. Then we also have the point 2, which is transparency and accuracy in PCF accounting. One of the standout features of PACT methodology is its ability to ensure transparency and accuracy in calculating a product carbon footprint, or PCF. Transparency is achieved by clearly defining the boundaries of what is included in the footprint, such as emissions from packaging, logistics, and even carbon capture technologies. Accuracy is ensured through rigorous data collection and categorization, which minimizes uncertainty and allows for reliable comparisons between products and industries. Let's go to the next point, which is our key point 3, emissions categories in PACT. The methodology organizes emissions into specific categories to make the accounting process both structured and comprehensive. These categories include fossil emissions, which account for emissions from fossil fuels used in production, transportation, and other processes; biogenic emissions, which include both the emissions and removals associated with organic materials like biomass; land use change emissions, which track the impact of deforestation, agricultural expansion, and land use practices. packaging emissions, which focus on the materials used to package products from production to disposal. Outbound logistics emissions, which cover the transportation of products to their next point of responsibility. Aircraft greenhouse gas emissions, which specifically monitor emissions from air transportation. Finally, carbon capture and storage CCS and utilization CCU, which track emissions reductions achieved through cutting-edge carbon capture technologies. As you can see in the flow chart on the side, these categories provide a structured way to account for all relevant emissions, ensuring no major source is left untracked. Let me take you through these sources one by one. First, we have the key category, which is fossil emissions, which are emissions resulting from the use of fossil fuels. These include emissions from the production process, such as energy used in factories, as well as emissions from transportation, like fuel burned by trucks or ships. Fossil emissions are often the largest contributor to a product's carbon footprint, making this category a critical focus for emissions reduction efforts. Next, we have biogenic emissions, which refer to carbon dioxide emissions and removals associated with biomass and organic waste. For example, when wood or other organic materials are burned or decomposed, they release carbon dioxide into the atmosphere. On the other hand, if managed sustainably, biomass can also act as a carbon sink, removing carbon dioxide from the air. This dual nature makes biogenic emissions an important category to monitor, especially for industries like agriculture and forestry. The third category is land use change emissions, which track the environmental impact of activities like deforestation, agricultural expansion, and land management practices. When forests are cleared for farmland or urban development, the carbon stored in trees and soil is released into the atmosphere. These emissions are significant because they do contribute to global warming, but also lead to biodiversity loss and ecosystem degradation. Another important category is packaging emissions, which account for the greenhouse gases emitted during production, use, and disposal of packaging material. From plastic wraps to carbonated boxes, cardboard boxes, packaging plays a major role in supply chains. Monitoring these emissions helps companies identify opportunity to switch to more sustainable materials or reduce packaging waste altogether. Outbound logistic emissions focus on the transportation of products to their next destination, whether it is a distribution center, retailer, or end consumer. This category includes emissions from trucks, trains, ships, and other modes of transportation. With the rise of global trade and e-commerce, logistics emissions have become a growing concern, making them a key area for improvement, especially through innovation like electric vehicles or optimized delivery routes. The sixth category is aircraft greenhouse gas emissions, which specifically monitors emissions from air transportation. While air transport is often faster, it is also one of the most carbon-intensive modes of transport. It's worth noting that PACT excludes radiative forcing effects from this category, which are additional warming impacts caused by aircraft emissions at high altitudes. Even so, this category is critical for industries relying on air freight or passenger transport. Finally, we have carbon capture and storage, CCS, and carbon capture and utilization, CCU. This category tracks emissions reductions achieved through technologies that capture carbon dioxide before it is released into the atmosphere. For example, carbon capture systems can be installed at power plants or industrial facilities to trap carbon dioxide and either store it underground or use it in other processes, such as manufacturing. The inclusion of this category highlights PACT's forward-thinking approach, recognizing the role of innovative technologies in achieving net zero emissions. While the PACT methodology provides a robust framework for monitoring greenhouse gas emissions, it is important to acknowledge that no methodology is without its limitations. Understanding these gaps allows us to identify areas for improvement and explore complementary approaches to address broader environmental impacts. Our key point one, no direct mention of solid or liquid effluent waste. This is one of the most significant gaps in the PACT methodology. While it excels at attacking emissions related to greenhouse gases, it does not explicitly account for the environmental impacts of waste materials such as industrial wastewater, hazardous liquids, or solid waste generated during production processes. This omission means that industries with significant waste streams, such as manufacturing, mining, or agriculture, may need to rely on additional tools or methodologies to fully capture their environmental footprint. Then the next key point is about focus primarily on carbon footprint and GHG emissions. This is a limitation in the methodology. While this focus is critical for addressing climate change, it does not fully encompass other environmental impacts, such as water pollution, soil contamination, or resource depletion. For example, the disposal of solid waste in landfills or the release of untreated wastewater into the rivers has significant environmental consequences that are not directly addressed by PACT. Our next key point is waste-related emissions are indirectly included. That said, it is worth noting that some waste-related emissions are indirectly included with the PACT framework. These included packaging emissions, which account for the production, use, and disposal of packaging materials, land use and waste management practices, which track emissions from activities like deforestation or landfill management, transportation of waste material, which includes emissions from moving waste or recycling facilities, landfills, or other disposal sites. While these categories touch on waste-related emissions, they do not provide a complete picture of the environmental impacts associated with solid and liquid waste. Having discussed the PACT methodology and its focus on greenhouse gas emissions, Let's now broaden our perspective to consider the distribution of environmental impacts across different types of waste gases, liquids, and solids. Understanding how each contributes to environmental challenges is crucial for developing comprehensive sustainability strategies. Here are our key points. Number one, different contributions by waste type. Environmental impacts arise from various waste types, each contributing differently to the overall picture. Gases, liquids, and solids all play distinct roles in affecting ecosystems, human health, and the climate. The relative contributions of these waste types can vary significantly depending on the sector and region. For instance, industries like manufacturing, agriculture, and energy production each have unique waste profiles that influence their environmental impacts. Gaseous emissions dominate global impacts. Globally, gaseous emissions are the most significant contributors to environmental impacts, accounting for approximately 50 to 70%. This dominance is primarily due to the widespread nature of greenhouse gases like carbon dioxide and methane, which have far-reaching effects on climate change and air quality. These emissions are particularly prevalent in energy-intensive sectors such as fossil fuels, power generation, and transportation, where they represent a major challenge for sustainability efforts. Liquid effluents in water-intensive industries are particularly significant, where they contribute 20 to 30% of environmental impacts. Industries such as agriculture, mining, and chemical manufacturing often generate large volumes of wastewater, which can lead to water pollution, habitat generation, and health risks if not properly managed. Addressing the impacts of liquid effluents involves improving water treatment processes and reducing pollutants at the source. Our key point 4 is solid waste and its localized impacts. Solid waste accounts for about 10 to 20% of environmental impacts, while its contribution is lower on a global scale. Solid waste has persistent and localized effects, such as land degradation, resource depletion, and pollution from landfills. Managing solid waste effectively requires strategies like recycling, composting, and waste-to-energy technologies which can mitigate these impacts and promote resource efficiency. In summary, understanding the distribution of environmental impacts across gases, liquids, and solids allows us to tailor our sustainability efforts more effectively. By recognizing the dominant role of gaseous emissions and the significant contributions of liquids and solids, we can develop comprehensive strategies that address the full spectrum of environmental challenges. Next, we will explore how integrating these insights into environmental management practices can drive more sustainable outcomes across industries. To conclude, let's summarize the key takeaways from this presentation and outline some recommendations for addressing the environmental challenges we have discussed. The insights we have covered highlight the importance of a comprehensive approach to environmental impact assessment and management. First, let's recap the main points. The PACT framework provides a robust system for accounting for greenhouse gas emissions. However, it does not currently address other critical forms of waste such as solid and liquid waste, which also contribute significantly to environmental impacts. Gaseous emissions dominate global environmental impacts, particularly in terms of climate change and air quality. In contrast, liquid effluents and solid waste have more localized effects such as water pollution, eutrophication, and land degradation. These localized impacts can accumulate over the time and, in some cases, extend to regional or global scales, as seen with microplastics and ocean pollution. So, given these observations, here are three key recommendations moving forward. Expand the PACT to include metrics for solid and liquid waste. While PACT is highly effective for GHG emissions, expanding its scope to include metrics for solid and liquid waste would make it a more comprehensive tool for evaluating environmental impacts. This would provide organizations with a fuller picture of their environmental footprint and help guide more holistic sustainability strategies. Then, use complementary methodologies for broader evaluations. To address the limitations of PACT, we recommend integrating it with complementary methodologies such as life cycle assessments, LCA. LCA evaluates the environmental impacts of a product or process across its entire life cycle, from raw material extraction to disposal. This approach ensures that all forms of waste, gaseous, liquid, and solid, are accounted for, providing a broader perspective on environmental performance. Next, focus on sector-specific solutions. Finally, targeted sector-specific solutions are essential for reducing emissions and waste. For example, in the energy sector, transition to renewable energy and improving efficiency can reduce gaseous emissions. In agriculture, better water management and sustainable farming practices can address liquid effluents. In manufacturing, waste recycling and cleaner production technologies can minimize solid waste. Tailoring solutions to the unique challenges of each sector will maximize their effectiveness and drive meaningful progress. In summary, the PACT framework provides a strong foundation for addressing greenhouse gas emissions, but expanding its scope to include solid and liquid waste is essential for more comprehensive environmental strategy. By integrating complementary tools and focusing on sector-specific solutions, we can tackle the full spectrum of environmental challenges and move closer to achieving sustainability goals. Thank you for your attention, and I look forward to your questions and insights.